choosing the right negative and positive controls. The backbone of valid experiments. Today we're going to discuss a topic that can truly make or break your experiment: controls. It doesn't matter whether you work in biology, public health, engineering, artificial intelligence, psychology, economics, or environmental science. If your controls are weak or poorly designed, your conclusions become unreliable. But when your controls are strong, your data becomes far more meaningful and trustworthy. This is one of the most fundamental and universal principles in scientific research. What is a control? A control is a comparison standard used to validate experimental results. Controls help us answer one fundamental question: is the effect we observe truly caused by our intervention, or could it be due to something else? Without controls, we only observe change. With proper controls, we can establish causality. Why controls are critical? Controls are critical in any experiment. Without proper controls, there is no way to establish causality, no confidence in the results, and ultimately, no publishable outcome. If you cannot separate cause from coincidence, you do not have science, you have speculation. In fact, reviewers often examine the controls first, even before looking at the main results. Types of control. Each type of control answers a different validation question. You must choose the right control based on your study design. Negative control. Negative controls test whether your system is stable and unbiased. If something changes when nothing should change, that's a red flag. Why negative controls matter. Negative controls help detect critical issues in an experiment, such as noise, contamination, bias, and even system drift. If your negative control shows an effect, it is a warning sign that your system may be flawed. In public health, this could indicate survey bias. In artificial intelligence, it may point to data leakage. And in engineering, it could reveal a calibration error. Positive control. A positive control is a condition where an effect is expected. For example, in biology, it could be a known active drug. In social science, a validated behavioral intervention. In engineering, a known stress threshold. And in artificial intelligence, an established benchmark dataset. Positive controls answer a critical question: is my system capable of detecting a real effect? If your positive control fails, it means your system lacks sensitivity. Why positive controls matter. Positive controls confirm three important things in a system: sensitivity, responsiveness, and functionality. Imagine testing a thermometer. If you place it in boiling water and it does not show a high temperature, you cannot trust it under normal conditions. That is exactly the purpose of a positive control. Interpreting controls together. When interpreting results, controls must be considered together. In an ideal pattern, the negative control shows no change, the positive control shows the expected change, and the treatment provides the meaningful comparison. Controls work as a system. The negative control shows stability. The positive control shows sensitivity. And the treatment reflects your hypothesis. Remove any one of these, and the interpretation becomes weaker. Biological example. Here is a biological example. Imagine testing an anti-inflammatory compound. The negative control would be untreated cells. The positive control would be a known anti-inflammatory drug, and the treatment group would receive the new compound. If the untreated cells reduce inflammation, something is wrong with the system. If the known drug fails to show an effect, the system may not be working properly. But if the new compound behaves like the positive control, that is a promising result. Social science example. Here is an example from social science. Imagine testing a mindfulness intervention. The negative control group receives no training. The positive control group receives an established therapy, and the treatment group participates in the new program. In psychology or education research, this design helps prevent placebo or expectation effects from leading to misleading conclusions. Public health example. Here is an example from public health. Imagine evaluating a community nutrition program. The negative control would be a community without any intervention. The positive control would be a proven public health program, and the treatment group would implement the new policy strategy. Public health studies often rely heavily on proper comparison groups to avoid confounding factors. Engineering example. Here is an example from engineering. Imagine testing material durability. The negative control would be the standard baseline material. The positive control would be a material known to fail under certain conditions. And the treatment group would be the novel composite being tested. Engineering research also depends on benchmarking. Without a baseline comparison, innovation cannot be properly quantified. AI, machine learning example. Here is an example from AI and machine learning. The negative control would use random labels. The positive control would use a benchmark dataset. And the treatment would be the new algorithm being tested. AI systems must demonstrate performance that is better than chance. If your model performs similarly to random labels, it means the system is not truly learning. Vehicle and sham controls. There are also specialized types of controls, such as vehicle controls and sham controls. A vehicle control uses the solvent or delivery medium without the active compound. A sham control involves a fake or simulated procedure. Vehicle controls help isolate the effect of the delivery system. Sham controls help isolate the effects of the procedure itself. For example, in surgical trials, sham procedures are used to test the influence of placebo effects. Human clinical trials. Here is an example from human clinical trials. The negative control is typically a placebo. The positive control is the standard of care treatment, and the treatment group receives the experimental therapy. Clinical trials require careful ethical consideration. Placebos cannot replace an effective therapy. Ethical considerations. Ethical considerations are essential when designing studies that use controls. These include not withholding effective care, ensuring transparent and informed consent, and maintaining a careful balance between risks and benefits. Controls must never violate ethical principles. Scientific rigor must always align with human responsibility. Multi-arm design. Some studies use a multi-arm design. These may include a placebo group, a low-dose group, a high-dose group, and a group receiving the standard therapy. Complex studies often include multiple controls. This approach improves interpretability and helps clarify dose-response relationships. Statistical implications. Controls define the comparisons in a study. If the controls are incorrect, the statistical results become invalid. Your statistical model depends on the structure of the controls. A wrong control leads to a wrong comparison, and ultimately to misleading p-values. Confounding variables. Confounding variables can strongly influence study results. These may include factors such as age, sex, environment, or batch effects. Controls must closely match the characteristics of the treatment group. Otherwise, any observed differences may come from confounding factors, not from the intervention itself. Reviewer perspective. From a reviewer's perspective, controls are one of the first things evaluated. Reviewers often ask, are the controls appropriate? Are they sufficient? And are the comparisons valid? Many manuscripts are rejected because of weak controls, not weak data. Controls ultimately determine the credibility of a study. Real-world failure example. Real-world failures in research often highlight the importance of proper controls. Poor or missing controls can lead to retractions and findings that cannot be reproduced. Many high-profile failures in science can be traced back to inadequate controls. Strong controls help protect both the integrity of the research and the researcher's reputation. Cross-disciplinary reminder. Controls are a universal principle across many disciplines, including biology, public health, engineering, economics, artificial intelligence, and psychology. Whether you're testing a vaccine, a bridge material, an AI algorithm, or a policy change, controls are what validate your claims. Checklist before starting experiment. Before starting an experiment, ask yourself a few critical questions. Is my negative control appropriate? Is my positive control validated? Is the comparison fair? And are confounding variables minimized? Before collecting data, pause and review this checklist. If it is incomplete, redesign the experiment now, not after the results. Controls are the backbone of valid experiments. If you want us to create a detailed episode specific to your discipline, clinical research, AI, public health, engineering, psychology, tell us. Science becomes powerful when it becomes controlled. If you enjoyed this video, found the topic helpful, or believe this content could be useful to others, please take a moment to like, share, and leave a comment below. And don't forget to subscribe to the channel for more videos like this. Thank you for watching.